A very good day, Professor Dr. Kairul, myself Saravanan, and my team member Shanice and Zaim. And our project title will be Optimization of Tip Cavity Design for Enhanced Cooling Efficiency in Turbine Blade. And project leader will be myself, and our collaborator Unical Mead, Boeing, GE Aerospace, and Emirates. So the total project cost will be RM 100,000, and then proposed project duration will be 18 months. So for the introduction for our project, mainly we all know the gas turbine engines are vital power sources for aviation and electricity generation, operating under extremely high temperature that often 1500 degrees Celsius. So these temperatures surpass the melting limits of superalloys used in the blades, making effective cooling essential for the blade longevity and engine reliability. So cooling is achieved through a combination of internal cooling channel, film cooling holes, and then the blade tip cavity, a small recessed region near the blade tip that plays critical role in controlling airflow. Specifically, the tip cavity manages the tip leakage flow, the air that leaks from the high pressure side to the low pressure side over the blade tip. So this leakage creates the vortex leading to aerodynamic losses, elevate the temperatures, which negatively affect engine efficiency, and then include the blade durability. So optimizing the tip cavity design is therefore key to minimizing leakage and enhancing the cooling. However, this is a complex challenge due to the turbulent flow, heat transfer interaction, competing requirement for aerodynamic efficiency and thermal protection. So for the importance of tip cavity is essential but often underestimated component in turbine blade cooling design. So the main function of the tip cavity is to manage the tip leakage flow, the air that escapes from the high pressure side of the blade and to the low pressure side of the blade due to the pressure difference. So this leakage flow is major source of aerodynamic inefficiency of turbines. When tip leakage airflow uncontrolled, it forms strong vortex. This vortex not only represent a loss of useful engine power but also elevate local temperature around the blade tip, creating hot spots that can accelerate the thermal fatigue, material degradation. In addition to causing aerodynamic losses, the leakage flow can disrupt the intended cooling airflow pattern, reducing the effectiveness of the blade's cooling system and putting structural integrity of the blade at risk. Therefore, the design of the tip cavity directly influence two critical aspects of turbine performance. One is aerodynamic efficiency and thermal protection. So an optimized tip cavity can minimize the leakage by disrupting or controlling vortex formation. This allowed a proof sealing of the blade flow path. So at the same time, it can enhance the distribution of cooling air around the tip, preventing localized heating and ensuring longer blade life. So achieving this balance poses
Current turbine blade tip cavity designs crucial for cooling and aerodynamic efficiency are limited by traditional shapes that inadequately balance reducing tip leakage and maximizing cooling. Existing approaches typically addresses either aerodynamics and cooling separately, lacking a comprehensive framework that integrates aerodynamic, thermal, and structural factors. Complex turbulent flow and heat transfer inside the tip cavity are difficult to predict and optimize due to limitations in experimental and computational methods. Although additive manufacturing could enable innovative cooling geometries, it remains underused in this area. There is a critical need for integrated multidisciplinary optimization framework using advanced simulation and additive manufacturing to develop validated high-performance tip designs. This is essential for creating the next generation of turbine blades, higher efficiency, durability, and lower emissions. The proposed research aims to develop such an integrated approach combining CFD modeling, multi-objective optimization, and additive manufacturing prototyping. The research aims to optimize turbine blade tip cavity design to enhance cooling efficiency and reduce aerodynamic losses, improving gas turbine engine performance and durability. Key objectives include conducting parametric CFD simulations to study how geometric factors affect thermal and aerodynamic behavior. Secondly, analyzing flow and heat transfer under realistic high temperature, high pressure conditions. Thirdly, applying multi-objective optimization techniques to find design balancing cooling and aerodynamic performance. Thirdly, fabricating selected optimal designs via additive manufacturing for empirical validation. And lastly, developing practical design correlation and guidelines from combined simulation, experimental, and optimization results. This comprehensive approach integrates modeling, manufacturing, and testing to create practical advanced tip cavity designs, addressing current technology gaps and promoting efficient and sustainable turbines. This research project is structured around 18 months timeline covering all key phases from conceptualization and final validation. The scope includes comprehensive literature review, development of high-fidelity CFD models, multi-objective design optimization, additive manufacturing of optimized blade tip cavities, and experimental validation through thermal and aerodynamic testing. Collaboration with university laboratories, aerospace test center, and industry partners will provide the necessary expertise and advanced facilities to support each phase. However, some limitation must be acknowledged. Experimental tests will be conducted on scale prototypes rather than full-scale blades due to budget and facility constraints. As such, results will require careful extrapolation to real-world turbines conditions. CFD simulation will utilize quasi-steady assumptions to manage computational resources, which may simplify some transition phenomena. Despite this limitation, the integrated computational and experimental approaches ensures the development of practical, validated design insights that are highly relevant to next-generation turbine blade cooling technology.
In this research, the methodology followed the structured and systematic approach to optimize the turbine blade tip cavity, enhance cooling efficiency and aerodynamic performance. The process begins with parametric CAD modeling, where different cavity geometries are created by varying parameters such as cavity depth, width, shape, and rim features. These designs are then evaluated using conjugate heat transfer CFD simulations, which analyze both fluid flow and heat conduction under realistic turbine operating conditions, including temperature gradients and pressure differences. To efficiently explore the large design space, a design of experiments method is applied, allowing for strategic selection of geometric variations while minimizing the number of simulation runs. Based on the CFD data, surrogate models are developed as fast, accurate approximations of the simulation results, enabling quick evaluation of numerous design candidates. The optimization is carried out using the NSGA tool, which handles multiple objectives simultaneously, maximizing cooling effectiveness while minimizing aerodynamic losses to produce a Pareto front of optimal solutions. Then the most promising designs are then fabricated using selective laser melting additive manufacturing, which enables the creation of complex city shapes beyond traditional machining limits. Finally, the prototypes undergo experimental validation through thermal imaging and pressure measurements to confirm both cooling performance and flow characteristics. This integrated methodology, combining simulation, optimization, fabrication, and testing, ensures a comprehensive, realistic. So in this research, the CFD is a central tool which is going to be used to analyze the complex flow and heat transfer phenomena occurring inside the turbine blade cavity, and it allows us to create a detailed physics-based numerical model of the fluid flow and temperature fields interacting with the blade geometry. So we are going to employ the conjugate heat transfer simulations, which means that both the fluid flow in the cavity and the heat conduction through the blade material are modeled simultaneously. And this approach is important because the thermal performance depends not just on the coolant airflow but also on how heat travels within the solid blade. And then to replicate the real turbine operating conditions, the simulations incorporate carefully defined boundary conditions. These conditions will include high temperature gas flows on the blade's exterior surfaces, cooling air injected inside the cavity, and pressure differences between the blade's pressure and suction size that drive leakage flow. The CHD model is going to capture intricate vortices and turbulence near the cavity, which are responsible for tip leakage losses and evaluated surface temperatures. And it's also going to track how effectively the coolant air extracts heat from the blade metal. And then by analyzing the simulation results such as velocity vectors, temperature contours, and pressure distributions, we are going to assess how different cavity geometries affect.
For the optimization technique, optimization of turbine blade tip cavity design involves balancing multiple, often conflict objectives, primarily maximizing cooling efficiency while minimizing aerodynamic losses. To achieve this, we employ a multiple objective evolutionary algorithm called non-dominated Southing genetic algorithm 2, NSGA2. This algorithm mimics natural selection by evolving a population of design over successive generations, selecting and combining the best performing candidates. We start by defining key geometric parameters of the tip cavity such as depth, width, shape features, and set reasonable bound for their variation. Using design of experiments, we run selected CFD, cumulative fluid dynamics simulations, to explore how these parameters influence performance. The computational cost of running full CFD simulation on every design iteration will be prohibitive. Therefore, we build surrogate models, statistical approximation that predict cooling efficiency and aerodynamic loss based on geometric parameters, allowing rapid evaluation of many design variations.
Additive manufacturing, particularly selective laser melting (SLM), offers significant advantages for fabricating optimized turbine blade tip cavities that traditional manufacturing methods cannot achieve. SLM builds parts layers by layers from metal powder using a laser, enabling extremely complex and precise geometries. This flexibility allows realization of intricate internal cooling channels, sharp cavity edges, and shapes tailored to enhance airflow and thermal management. Such complex designs are key to achieving improved cooling performance and aerodynamic efficiency, features often impossible or prohibitively expensive to produce using conventional machining or casting. Moreover, additive manufacturing facilitates rapid prototyping, which accelerates the design validation cycle. Optimal design from computational models can be quickly transformed into physical prototypes for experimental testing. This integration of advanced manufacturing are high-fidelity simulation breaks previous design constraints, unlocking new performance levels in turbine blade cooling technologies and contributing to more efficient, durable engines.
So to validate the optimized turbine blade tip cavity designs, experimental testing is essential to ensure that simulation predictions and translates to real-world performance. The fabricated prototypes will be installed in a specialized test rig which is designed to replicate key operating conditions of gas turbine, including realistic temperature gradients and pressure differences across the blade tip region. The thermal imaging cameras will be used to capture detailed high-resolution surface temperature maps of the blade tip. This infrared thermography provides specially resolved data showing how effectively each cavity design cools the blade, pinpointing any hotspots or temperature variations. In addition, precise pressure sensors will be strategically placed around the blade tip cavity to measure aerodynamic flow characteristics. These measurements help to identify areas of tip leakage flow, vortex information, and associated aerodynamic losses. Together, these experimental measurements allow us to compare actual physical behavior with the computational fluid dynamics and predictions, providing critical validation of simulation models. By integrating experimental data with simulations, we can refine and improve the models by increasing their accuracy and confidence for future design iterations.
This research aligns with Malaysia's national strategic priorities, particularly the National Innovation Policy, which aims at fostering high-tech industries such as aerospace and advanced manufacturing. By enhancing turbine blade cooling efficiency and reducing aerodynamic losses, the project promotes cleaner energy production and supports Malaysia's commitment to sustainable industrial growth. Additionally, it contributes to international goals, which is the United Nations Sustainable Development Goals SDG 7, SDG 9, and SDG 13, which is the climate action through innovation that improve energy efficiency and lower emissions. Thus, this work bridges advanced engineering innovation with environmental sustainability, which is reinforcing Malaysia's role in global clean technology leadership.
This project aims to achieve significant advancements in turbine blade tip cavity technology. The primary expected outcome is at least a 15% improvement in cooling efficiency, leading to better thermal management and longer blade life. Additionally, the project targets a reduction of up to 8% in aerodynamic losses, directly contributing to a higher engine efficiency and lower fuel consumption. Beyond these performance gains, the research will generate new empirical design guidelines and modeling tools that can be adopted by the industry for future blade designs. It also has the potential to produce valuable intellectual property, such as patents for novel cavity geometries and manufacturing methods. Overall, the outcomes will strengthen Malaysia's aerospace R&D capabilities and foster innovation and support the development of more sustainable and cost-effective gas turbines with reduced environmental.
So for the timeline and budget for our project, the research project is planned over an 18-month timeline structured into 4 key phases. The first key phases: literature review, parametric modeling, initial CFD simulation. The second phase involves detailed CFD analysis, surrogate modeling, and multi-objective optimization of tip cavity design. In the third phase, optimized design will be fabricated using additive manufacturing and prepared for experimental testing. The final phase concentrates on rigorous experimental validation, integration of results to finalize the design guidelines and disseminate findings. So overall, for the total budget for the project is approximately RM100,000 allocated to personal computational resources, additive manufacturing, experimental setups, and dissemination activities, including publication and conference. So this structure is timeline and budget ensure for the balanced focus on both computational experimental efforts and leading robots. So validate outcomes within the plan and duration. So our budget for separately will allocate for personal will be 40,000, computational resources will be 15,000, prototype fabrication 20,000, experimental testing will be 15,000, and then for the travel and contingency will be RM 10,000.
To conclude, this research offers a novel and integrated strategy for optimizing turbine blade cavity design, focusing on balance, enhanced cooling efficiency, and minimize aerodynamic losses. The approach combines high-fidelity CFD simulations, sophisticated multi-objective optimization, advanced additive manufacturing, and thorough experimental validation to overcome current design limitations. Successful implementation promises significant improvements in turbine performance, which extending blade lifespan and reducing fuel consumptions and emissions. This work not only advances turbine technology but also support national innovation and sustainability agendas contributing to cleaner and more efficient energy systems. Thank you.